Welcome to N is for Networking. We are introducing IPsec for you today, and this is at Holly's request. Wait, who am I? I am Ethan Banks. And who's Holly? Holly is Holly Metlitzky. I'm an IT veteran. I've been doing networking stuff for 30 years. And Holly, it's been 2 years you've been at this networking thing, something like that, roughly? Okay. You can follow Holly and I via LinkedIn and the Packet Pusher Community Slack group, and please do. And Holly and I go back and forth on concepts in the wonderful world of data networking. In theory, I know what I'm talking about, and so Holly asks me questions, and yeah, we have those kind of conversations. And Holly, you brought up IPsec, that you wanted to talk about IPsec. Why? What brought IPsec to your mind?
This is one of those topics that I've touched and configured, but never got the background to, which is something I speak about a lot. I've set up an IPsec tunnel with no background into actually studying IPsec. So I thought this is a great way to go back to step one and learn something about IPsec without just being like, yes, look, it works and it does what you intended to do.
Okay, so give me some background then on what you've been using IPsec for, and what you think you know about it so far.
So, I mean, I used it for one specific use case with a customer who asked me to set up an IPsec tunnel from, I think it was their branch office to their HQ.
Mm-hmm.
That was it. And we set up the tunnel. I configured it in the CLI, got some keys, some encryption, configured it, and then it worked.
Got it. So, okay. So you followed some kind of was this all with all Juniper gear then? Since you're a Juniper person. Yeah. Okay. So Juniper to Juniper box with IPsec, you built the tunnel, connected them, and just curious, were you punching a routing protocol through that tunnel, using it like a kind of like a WAN interface, or?
No, we weren't actually. It was very basic. I think it was all layer 2 stuff.
Okay.
Possibly.
Maybe, yeah.
But we definitely didn't configure any routing protocols.
Depending on your encapsulation type, but yeah. Okay, so let's start at the very, very beginning. IPsec stands for IP security, and you're accomplishing a couple of things here. You're adding trustworthiness and secrecy to your communications that are using internet protocol, because by default, IP doesn't have either of those things. You don't 100% know who you're talking to, and your communications are out in the open if you're using just IP by itself. And so IPsec is a way that you can know who you're talking to, be confident in who it is that you're talking to on the other end of the conversation, and that your conversation is secret if you want it to be secret. You don't have to use IPsec that way. There's, as far as secrecy goes, there's some options there that we're going to talk about. But that's the big idea. And that matters when you're going across an untrusted network like the internet. Now, you set up that IPsec tunnel. Was the internet what you were using to connect those two offices?
Yes.
Okay. And so probably a couple of SRX firewalls maybe sitting at the edge? And you set up an IPsec tunnel? Okay. Between those two, between the public interfaces of the SRX?
Yes.
Of the SRXs? Sure. Okay. Got it. Classic kind of a setup. Exactly the kind of scenario where you very commonly see IPsec used. All right, so I said trustworthiness and secrecy, and if we were to map those more or less plain English words into technical words, IPsec is adding authentication, just like we'd use passwords and two-factor authentication and so on to prove who we are to an application so that we can log into the thing. It's kind of like that. We're talking about authentication. And then encryption. We're using math to cipher our packets in such a way that we two are the only ones who can decipher each other's packets. So there's a lot of math going on to make that happen. Take a packet that we could read ordinarily, use math to cipher it. So now it's this unreadable code, just a bunch of letters and numbers that math has turned it into, that no one else can read unless you've got the right key on the other end. So we're giving trustworthiness and secrecy to the communications, and we're doing it with authentication and encryption to make all of that happen. Those are the big ideas. How are you feeling so far?
Yeah, 100%. when I think about it and we discuss it in these terms, I'm like, well, this kind of seems like a best practice. I don't want anybody being able to look at all my packets, but I know that, IPsec is obviously not a standard that everybody's going to implement.
Well, it adds complexity to your
Yep.
network, right? It adds overhead because now you've got to manage keys. Now you've got you're asking the devices that are in either end of the IPsec tunnel. Typically, it's implemented as a tunnel, though it doesn't have to be. But you're asking either device on either end of the tunnel to have to encrypt and decrypt packets, which adds a burden to the CPU that's there. Although IPsec is so common that there are a lot of chips that are put into network devices that just make it easy for that device to do that. You're not asking the CPU, the general purpose CPU, to do that math. You've got some special piece of silicon that's doing that math and means you can pump a lot of traffic through that IPsec tunnel without it being a lot of overhead. But still, it's one of those things you got to think about. As far as it being a best practice, because of that overhead and complexity that gets added, you have problems like key management. Okay, now I got to deal with keys, or because keys are being exchanged on either end, you got to keep track of that stuff. And a best practice would be to rotate those keys now and again. Maybe you're using certificates instead of putting in keys, like you probably sounds like what you did in your scenario. Certificates expire. You've got to maintain a certificate infrastructure to issue new certificates that are being used instead for that authentication process. It's a thing. It's a whole thing. That said, you're not wrong in that, like, why wouldn't you want to do this? For example, wireless communications and Wi-Fi. Those communications are always encrypted.
Yeah.
Anything over the air that you could grab with the right antenna and see those packets, you'll see that all Wi-Fi communications are encrypted. But let me put the question to you. Let me put a different question to you, and maybe make you rethink whether or not IPsec all the time would be a best practice. We've got HTTP and we've got HTTPS. Do you ever see HTTP, plain text HTTP, in use these days?
No, not really.
Not really. I mean,
Yeah.
it exists. It's a thing, but hardly ever. Almost every website now is HTTPS, HTTP secure, meaning it's not IPsec, but the packet payloads are encrypted in a different way. So what am I getting as a benefit if I add IPsec to that HTTPS transaction? I'm not saying there's no benefit, but but it is much less of a benefit, right?
Yeah. So in the world of HTTP, it would make sense to have some sort of other security protocol protecting that. But when the payload's already encrypted, it's, double
Payload's
security.
encrypted. Yeah, you kind of, and from a mathematical perspective, when you're encrypting an already encrypted packet, it's a thing that you can do, but sometimes you end up with like bigger packets than you started off with, and then you're adding this double encryption decryption burden to various points in the system. And so the question becomes, why am I doing this? And maybe there's a reason and maybe not, but generally speaking, the need for encryption across the wire via IPsec is much less if you're already using an encrypted communication protocol like HTTPS, the most common ubiquitous protocol in use across the internet for communications, that is handling authentication for you, because the server presents a certificate to you. Look, I'm me. You can trust me. See the certificate? It's a valid certificate that you know because of the certificate stores that are inside your browser that you know you can trust. And I've got a valid expiration date and all of these things. So you know who you're talking to on the server end, and you've got encrypted communications. The server doesn't care who you are so much. It just wants to talk to you, but at least you know the server you're talking to is trustworthy. IPsec means both ends of the tunnel know who they're talking to. They've authenticated to each other. So, okay, Holly, I want to get into why. Where would you do this? And we want to set this up by talking about what do we mean by trustworthiness, and then what do we mean by secrecy. So with trustworthiness, what I'm getting at is How do you know you're talking to who you think you're talking to on the internet? How do you know that no one messed with the traffic along its way to you? Because if you get into cybersecurity, there's a zillion different kinds of attacks and bad things that can happen to your traffic going across the public internet. And IPsec is designed to help you with those specific situations. And so, let's talk through some of those
Yeah.
things. IPsec provides authentication, and then integrity would be another word, meaning the packet hasn't been messed with. Authentication, we know who we're talking to because we presented credentials of some kind, a key, a certificate, something. And that those things, authentication and then integrity, we know the packet hasn't been messed with, means there's a whole bunch of common attacks that should be foiled by the use of IPsec. So, for example, a man-in-the-middle attack. Do you know what a man-in-the-middle attack is?
Yeah, I enjoy the terminology because it's one of those things that actually is exactly what it sounds like.
Yep.
So somebody, a third party, from when your traffic is flowing between A to B, has, I guess, I'm losing my words here, but has inserted themselves or has done something with your traffic before it's gotten to the other side.
Yeah, somehow they've gotten in the middle of your conversation, and it could be because the attack happens at an internet service provider and an exchange point on the internet that your traffic happens to be flowing through that somehow they've gotten access to. There's various other ways with IP address spoofing and faking that they themselves are someone that they're not can get in the middle of your conversation. So exactly as you put it, they're in the middle of your conversation. Your traffic is flowing through them. They're in the middle, and now they're hoping to be able to mess with stuff, change things. A man-in-the-middle attack could be looking at a DNS response that is coming through. Hey, I need the IP address for this host name. The DNS server responds with the proper IP address. The man in the middle sees that transaction and changes the IP address to an IP address of some malicious server. You get the malicious IP that was changed on the way back. Okay, if you're using IPsec, the math won't work anymore if that packet's been changed. There's a checksum math that goes against that packet. And if the packet payload is different now, the hash value is going to be different, and there'll be a detection on the other end. Hey, somebody messed with this thing. This isn't the same. This isn't the packet I was expecting to get because the math comes out differently than what I was expecting. I'm going to discard this packet. This is no good. So a man-in-the-middle attack should be able to be foiled that way. There's also, for sake of time, we're not going to get into all these, but I'm just going to mention, we got replay attacks, tampering modification, like I just mentioned, something that a man-in-the-middle might do, spoofing, someone pretending to be, by falsely using an IP address of the actual owner of that IP address. Spoofing, they're pretending to be someone else. Session hijacking, where a man in the middle actually takes over the session. So you're no longer, it's not that they're just in the middle looking at your conversation. They actually become the endpoint you're talking to because they've hijacked the session. IPsec, when properly implemented, is going to protect you against all of those kind of things. You know, because of the authentication scheme in place and the fact that there are integrity checks for the packet payload, that you're talking to who you think you're talking to, and that the packet hasn't been messed with along the way. So that's what we mean by trustworthiness. And if there's a scenario like I'm sending traffic across the public internet where bad people are and they might be doing bad things, maybe IPsec is indicated in that case. Yeah. Okay, so another thing, we talked about trustworthiness. Now let's talk about secrecy. And this is pretty straightforward. If I want my package to be secret, what am I getting at, Holly?
You want to make sure that the receiving party is the only party that can actually look at what is inside that packet.
Yeah, if someone else sees those packets as they go by, it's just cipher gobbledygook. You can't make sense out of it because you don't have the keys to be able to decrypt that and turn it back into what it originally was before it was ciphered. Yeah, we want our communications to be secret. Now, again, going back to the point I was making earlier, a lot of communications across the internet are already ciphered like HTTPS. And so from a standpoint of keeping the communications secret, adding IPsec doesn't really change the situation. It's not, as we haven't really improved it. Our communications were already obfuscated. They were already secret. There was always some kind of a cryptographic ciphering of our communications that was going on. But back in the day, history, yay! We we would do things like not everyone used SSH for command line to a remote system, for example. Telnet was still really common. If you look at Telnet in a packet sniffer, like we've talked about Wireshark and packet sniffing and so on, the characters you're typing at the keyboard actually show up in the Telnet session. And so if you could capture someone else's Telnet session, you could see things like, hey, there's their username and password right there in plain text. Well, you could make that, you could obfuscate that, make the communication secret by putting that Telnet session through an IPsec tunnel. That would be a way to do it. Nowadays, no one does Telnet. I mean, yeah, Telnet exists and it's a thing, but no one uses that, especially if they have any sense about security. You use Secure Shell, SSH, instead. The same experience, but with secrecy built in. But IPsec would do that for you if you've got a scenario where that's key. And so the things that we're preventing here, what we're describing, eavesdropping. If you're looking at cybersecurity, you'll see the keyword eavesdropping. Yeah, but someone, a packet sniffer that's reading your traffic, right? Another thing that's used here, another point of a attacker that would be coming against your network and doing that eavesdropping is they're doing network recon. They're trying to figure out what your network looks like. And so they're looking at the packets that they can see come through and go, oh, they've got a network that's 10.15.10. Interesting. And then they add that to the things that they know about your network. Oh, I see that they've got what appears to be a Linux system running this flavor of the kernel and so on, because they're doing some fingerprinting against you maybe. And they're doing as much recon as they can about your network by pulling all the information that they can pull out of the packets that they can see, and then build an attack profile, trying to figure out what your attack surface is and how they can go against that attack surface and find a way into your network. As much of that as if you obfuscate all of that with IPsec, you're reducing the attacker's ability to perform recon on your network, not eliminating it. An attacker can always do recon on your network, but there's different ways. But you've made it harder for sure. I mean, if you just have unencrypted traffic that says all the things and you just make it easy for them. At that point, you might as well just posting a sign on the outside. Hey, here's a lot of cool things about what's going on inside my network because I didn't cipher any of it. Enjoy.
I think one thing that is important to note, and I was actually discussing encryption specifically with a colleague last night, is that when you hear encryption, if you haven't really looked into the different types of ciphers, it sounds like, oh, well, it's encrypted. I can just find the key or whatever and revert it back. But it's not that simple. A lot of these encryption mechanisms are really, really complex. It's not like, oh, you just find what type of encryption it is and you can, reverse decrypt it. It's really complex, and it's just to note that it's not that it really is quite foolproof. It's too much hassle than it's worth.
You're exactly right, because there's multiple pieces to it. There's the particular cryptographic ciphering that is used, and there's a whole bunch of different schemes. We're not going to get into those details in this discussion because that's a whole other thing.
Yeah.
But you also need the keys, and there's typically a public and a private key that work together. You need to have both sides of that to be able to unlock that algorithm and decode in a particular way. So it's not merely that an algorithm was used to encode, it's that the algorithm is run with a pair of keys in mind that have to work together. And if you don't know those keys, all you can do is guess. You'll know the public key because that in public-private key infrastructure, you'll know the public side, but you got to figure out the private side that locks in for that particular conversation. You can try to brute force it. That is, I'm going to try this one. then I'm going to try this one, then I'm going to try this one. And if you've got enough time, thousands of years, maybe millions of years, depending on the complexity of the key, you could, in theory, finally found it on the 8 billionth attempt.
Yeah.
I figured it out. And then off you go. And there is genuinely some thought about that in cybersecurity where it's like, how complex should we make the key? Because what if the information that someone captures, what if they're willing to try to brute force this thing for a period of years? Is the information still good after 4 years? Would it be still interesting? Or if after, I'm picking 4 years at random, but if at the end of that 4-year period, would the information be no good and just irrelevant? So do we change the complexity of our cryptography to those are decisions that you can make, because the more cryptographic burden you put on the system, the harder it is to do, the more math you have to do, and therefore the more computationally intensive it is to get that stuff done. But it's exactly what you say, Holly. This is not trivial. This is not an easy thing. You just apply the right cipher and off you go, you can decrypt it. Nope. You got to have the keys, and you cannot figure out what those keys are without brute forcing. Have you heard of, I'm going to introduce something else here, quantum safe cryptography? Have you run across that term?
I have not. I think I've heard it vaguely, but I haven't actually dived into it.
It's been in the news a bit because as quantum computing is on the rise, this new way of doing compute with qubits, and they're coming up with quantum processors now and adding qubits to it. It's not for sure, but there is a theory that quantum, which does computing in a very different way from CPUs that we're used to these days, could brute force a key much more quickly, very quickly, in fact. So there's a theory that that would be a thing. And so when you read about quantum safe cryptography, it's talking about doing ciphers using keys, et cetera, in such a way that even quantum computing, should it actually become mainstream and usable by just about anybody, right now it's far too expensive, that they could begin hacking very quickly your ciphered communications using quantum. And so quantum safe cryptography is about using a cryptography scheme that is quantum proof. Even if you're using a quantum computer, you can't break my cryptography. Is the big idea.
At this point, if you're using a quantum computer, I don't think you really need to be worrying about breaking into anybody's packets or anything, but maybe further down the line.
Yeah, maybe. And it is somewhat theoretical. I haven't seen any proof of concepts for this. It's more a big idea that if you build a big enough quantum computer with enough qubits, you could get there. But right now, quantum computing is very, very expensive. It's only available to companies with typically multi-billion-dollar companies or research firms or government agencies that have huge amounts of resources. And you got to do crazy things like cool the quantum computer down to near absolute zero to be able to pull it off, and have a very particular kind of room, and then be able to do the work in a time that is quick enough that as the qubits decay, you're still getting a valuable result. It's hard. It's very early days for quantum, and we're a long way from, I can go to Amazon.com and buy myself a quantum computer. No, you can't. And I don't know what our lifetimes that we'll even see it, Holly. Maybe. That was a fun aside. Okay, so
back to IPsec.
Back to IPsec. So use cases for IP security, for IPsec. One of them, I think one of the biggest ones is exactly what you were describing. You needed to connect two endpoints together as basically a kind of a WAN link. Yeah, super common. We've been doing that forever. Some of the earliest things I did back in the day were exactly that. And what's funny about this is back in the day, if using IPsec to make a tunnel across the internet between two organizations was like, we don't have any money, so we're going to do this and hope it works, kind of thing, because the internet was considered unreliable and and so on. If you had money, you wouldn't stand up an IPsec tunnel across the internet. Instead, you'd buy a dedicated circuit from your internet, from your was going to say your internet service provider, but from your service provider that would provide you a private line, not internet based, but some like dedicated chunk of bandwidth, and then have a direct connection in, and that would be part of your network. If you were broke, because circuits were and still are, private circuits like that are expensive. Yeah, okay, we're just going to throw up the this tunnel across the internet because that's free. We already have the internet circuit and the firewalls, so we're just going to plumb that tunnel up and off we go. But nowadays, we're recording this in 2025. This is the most common thing in the world, and it's probably just as reliable and or more reliable than your dedicated private WAN circuit, and there's way more bandwidth to go with it. And so it's the most common thing in the world. And have we talked about SD-WAN on this show yet?
We've mentioned that we wanted to cover other topics before covering SD-WAN.
Ah, okay. This might be one of those topics because SD-WAN solutions, software-defined wide area network solutions, of which you at Juniper have a few different entrants in that space. Many of them use IPsec tunnels to connect SD-WAN routers together. Not all of them, because in fact, like at Juniper, you guys bought a company some years ago called 128T. If I remember right, they're not using IPsec to do their quote-unquote tunneling between SD-WAN
because
routers.
It's tunnelless.
It is tunnelless, and they're doing a different thing. So, of course, I picked the exception. But a lot of SD-WAN solutions, if you look under the hood, the way they're connecting to each other very often across the internet is using an IPsec tunnel. So a use case for IPsec is that is super common, exactly what you described early on, connecting a couple of offices together across the public internet.
So I've got a question going back to something you said earlier in the episode, and it's come back now. So you're referring to all of this as IPsec tunnels. And I love tunnels. So
I know you do.
You did make a comment saying it could be a tunnel or it may not be a tunnel. When is IPsec a tunnel and when is it not?
There are two ways you can implement IPsec, transport mode and tunnel mode. In transport mode, you are adding features to the existing packet to perform, to add trustworthiness to the packet, but you're leaving the packet otherwise intact. In tunnel mode, you are encapsulating the original packet inside of another packet. And performing an encryption there. So we're going to dive into that a little bit more. So I have never seen IPsec used in transport mode in a production environment. I have only ever seen it used in tunnel mode. That doesn't mean people don't do it in transport mode. It's a thing. But the implementation for IPsec I've seen, it's always tunnel mode. Again, transport mode is a thing. It exists, but in my experience, you're always doing it in as a tunnel. Okay, so we're going to go back to that. We're going to wrap up our conversation with that. Just kind of kick that around in a little more detail. But just to complete the use cases thought, we talked about using it as a WAN link, like you described right at the top of the show. You could connect not just organizations within the same organization with an IPsec tunnel, but another common use case is connecting to different organizations that need to exchange data for some reason. So I stood up a lot of IPsec tunnels over the years with companies that were contracted to do work for my company. And so the way we'd connect to them would be an IPsec tunnel because we needed to exchange confidential information privately, but we didn't want to burn the money on a private WAN circuit to make that happen. So the way we did it was I, as a network administrator on the one side and some network administrator on the other side, would coordinate the information to stand up an IPsec tunnel between our organizations, and we do that. And that was, now we can use the internet, we can exchange the information we need to exchange, boom, off we go. B2B, business to business IPsec tunnel would be that use case. And then the final one that I think is super common is client VPN. I'm in the coffee shop. I work for company X. I need to connect to the data center at company X to get to whatever the application is that I need to get to do my job. How do I do that? Well, you've got some client that's built into your Windows box or your Mac, etc., and you fire that up and you pop in a username and a password, and you don't know, but what's actually happening under the hood is an IPsec tunnel is being stood up between your laptop and some VPN concentrator or firewall, and now you've got this secure pipe going across the internet so you can get at stuff that's inside your company. That's not as common as it was because of SaaS and all these applications being stood up in the cloud, where you don't need to connect to your company's key application that's hosted in the data center, somewhere at headquarters, because that model isn't as common as it used to be. 10 years ago, certainly 20 years ago, the most common thing in the world. Nowadays, if your company's using SaaS as your accounting provider or as your sales CRM solution, you probably HTTPS:// some kind of address that's just for your company, and you're hitting something in the cloud. So you don't need a VPN tunnel to connect to that. You've already got secure communications. Does that sound like kind of the use cases you were imagining for IPsec these days?
Yeah, that's everything I've run into with it. So I've definitely hit it. Like you said, the VPN, client VPN, you don't really think about what's under the hood, but anybody who I guess has been around for a little bit of time has run into that use case for sure.
And it's not the only way to do like a client VPN for sure. I mean, that is a common way, but there are various other, if you, again, look under the hood and see what the packets actually look like, there's different ways to do these things. There's such thing as an SSL VPN. There are non-IPsec ways to do similar things like WireGuard. WireGuard is super common right now. And if you look at what they're doing, they're all similar, but they may not be IPsec as far as that goes. The model may be the same. It kind of like, it feels the same, but the mechanics of what's actually going on are different. IPsec is a specific standard that's got RFCs behind it and rules that you need to follow to be interoperable with IPsec and so on. Like, you connected two different Juniper SRX firewalls together, but that Juniper SRX firewall speaking IPsec can talk to a Cisco box that speaks IPsec, or a Palo Alto Networks firewall speaking IPsec, and so on, because it's a standard. And it's been a standard that's been around for a very long time. All right, Holly, here's a question for you then. Is IPsec like one protocol? Is it like this one thing?
If I had to not have read our show notes, I might have said yes.
Did you cheat? Oh, no.
I think, like, in my head, I was like, well, it's a protocol that uses different types of encryption, but which I guess in turn would mean that it's not one single protocol because it's not always deployed in the exact same way.
Right. Yeah, IPsec is actually, I guess I'd define it as a suite of protocols. And so I'm talking about, if we look on the wire, what do we see? What do the packets look like? Now, if we take and we're going to talk about these in a second here, but if we take the packet stuff aside, IPsec also involves a bunch of cryptographic ciphers that are involved. There's a lot to IPsec. It's kind of a big stack of technologies together. This is a networking-centric show, and so I'm focused a little bit in this introduction to the topic on like the packety aspects of it. And so if we put the cryptography aside, for the moment, and we just talk about what IPsec is made up of, if we were to look at the wire at an IPsec transaction going by, you would see multiple different protocols. Let's walk through them real quick here. We've got IKE, Internet Key Exchange. We've got AH, Authentication Header. ESP, Encapsulation Security Protocol, and NAT-T, Network Address Translation Traversal. Those are all, and I don't even know if that's a complete list, but certainly those are the core technologies, different packets that you might see on the wire that if you were to pump it through Wireshark's packet decoder would be able to pick these up and tell you, oh yeah, that's an IKE packet. Oh yeah, that's authentication header, etc.
So you wouldn't necessarily see like IPsec packet, you'd see one of these.
Exactly right. And different of them are used depending on how you've implemented the IPsec connectivity between the two endpoints, or which phase of the IPsec conversation you're having. So let's take Ike, for example, Internet Key Exchange. There's Ike version 1 and Ike version 2 out there. Ike version 2 is most commonly implemented these days. It's a bit more efficient in how the packet exchange goes back and forth. That is UDP port 500. We've talked about TCP and UDP and other transports. And if you see UDP going across port 500, that is probably Internet Key Exchange happening. And Ike is used for a lot of stuff because when you're trying to establish an IPsec session between two endpoints, remember we talked about authentication, we talked about secrecy, right? Well, the two endpoints have got to agree on a ton of stuff. They got to exchange keys, passwords, or certificates, something to demonstrate that the other one really is who they say they are. They've got to agree on the cryptographic ciphers that are going to be used. Oh, well, I'm going to encrypt this way. Okay, I can encrypt that way. That's something I can support too. Let's use that. You got to agree on that stuff. You got to agree on what you're going to talk about. I want to exchange information with you about conversations between this block of IP addresses and this block of IP addresses. Well, I want to talk about those things as well, that we agree. And so Ike is the protocol that's used during the setup process to establish all of those things that you can get the IPsec security associations, the SAs, stood up. Or if you want to simplify that, just say the tunnel. The tunnel is a bit of a misnomer depending on how we're implementing IPsec, but typically speaking, it's reasonable to say the tunnel. But even within a single IPsec tunnel, you can have multiple SAs, security associations, things that you're going to talk about. Ike is where a lot of magic for IPsec happens to get that thing stood up. And if you're struggling to bring up an IPsec tunnel where it's failing probably during this process, during Internet Key Exchange and subsequent negotiations. And if you're like banging your head, like, why won't this tunnel come up? And you begin doing debugging. If you look at the debugs on Internet Key Exchange conversation that's happening, you'll probably find your clue in there. Oh, I have a typo in the network I want to exchange information about. I fat fingered something. And so one side thinks we're supposed to talk about. Done that? Okay. You been there?
Yep. Wrong IP by one number.
And what was the experience? What was happening to you?
Well, we couldn't stand up the IPsec, and we were like, why isn't this working? Everything's correct. You know, the keys match, whatever. But like something just isn't right. So we combed through the config and like, that's not the right IP.
And then both sides they agreed on a lot of other things like keys and ciphers and so on, but not what we're actually going to exchange information about. So the two sides were not in agreement on IP addresses because there was a typo in one of the IP addresses. Yeah. Yep. That's all part of Ike. That's all of that stuff is happening during the Ike session. Oh boy. If you go to actually, it's like, thanks, that doesn't all happen in Ike. Some of it happens in this other place. Okay, forgive me. I did a bunch of reading last night. So if I got a detail minutely, I used to teach this. I used to teach classes on VPN and firewall, but that was 20 years ago. So some of these details leave my mind. But as far as my memory goes, that is all Ike that is establishing all of that information. Okay. Let's move on to authentication header, IP protocol 51. Now, I said IP protocol 51. I didn't say UDP or TCP. Do you remember what IP protocol means, what that's all about?
Yes.
Yeah.
I know where this came up because I think it was the OSPF, one of the OSPF episodes. And I was like, why does it just have a number? But that's the port or, for that specific thing.
It's effectively, you're identifying a different transport. TCP has an IP protocol number. I think it's IP protocol 4. I think I didn't look that up before. This is it isn't TCP. It isn't UDP. It's a different IP protocol. OSPF is 89, right? IP protocol 89, I think. It's its own thing. It's got its own way of getting traffic back and forth. Well, authentication header is IP protocol 51, as it happens. ESP, Encapsulation Security Protocol, is IP Protocol 50. If you're looking at a packet sniffer, those kind of details matter. If you're very used to seeing TCP and UDP and you don't see TCP and UDP because you're looking at what the heck is IP Protocol 51? It's authentication header. That's what it is. It's a different thing. It's at the same level functionally as TCP and UDP. It's just a different one. It's just another thing that's less common. And so I raise that just so people aren't thrown if they're like, I want to look at IPsec in my Wireshark and see what's in there. It's not TCP. It's not UDP. Well, part of it is UDP 500. But when we get down to, we're past Ike, we've agreed on what we're talking about. Now we're starting to throw packets back and forth at one another. There's these two protocols, AH and ESP, are the two protocols that you might see that are like, yeah, now we're talking. Now we're exchanging stuff over IPsec. Now we've got our payloads that are actually moving between my two IPsec endpoints. That's what you'll see. You don't see authentication header much in my experience. In fact, I can never think of a time I've seen authentication header used on a production environment. It's, for me, in my personal experience, it's always been ESP. I'm always looking at Encapsulation Security Protocol, IP Protocol 50. And the difference between authentication header and Encapsulation Security Protocol, do you know what that is? Holly, what the big distinction is?
Yeah, I do. Well, I mean, again, it's in front of me, but if one doesn't mention encapsulation, one only says authentication header, and the other one by name is encapsulation security protocol. So
yeah, exactly. Yeah, exactly. So AH is you're using that because you want to know that the packet came from a known and a trusted source, and that the packet hasn't been screwed with in some way. But you don't care about encrypting the payload for whatever reason. But you want the additional confidence that you're talking to who you think you're talking to and that the packet hasn't been messed with. But encryption isn't a concern. Maybe because the packet's already encrypted and you don't have to worry about so you don't have to worry about obfuscating the payload or whatever your reasons are. There's less, again, going back through history, if you're worried about how much computational cost IPsec is adding, well, authentication has less. It's going to be less computational intensity because you're not encrypting the payload. However, again, real life and production networks and so on, it's going to be ESP because you're not going to do just authentication header. You also are going to want to encrypt the payload almost certainly. And again, with modern CPUs and modern silicon architectures where you can offload encryption to a chip that's dedicated just for the purpose of encrypting things and decrypting things, you're not paying there's not a big computational cost for that, so to speak, in that you got a chip dedicated to it in not all, but in many boxes, particularly bigger routers and firewalls and so on. They've probably got a chip on it that does it for you. ESP, there you go. You're going to encrypt the payload as well. You get everything authentication header offers to you, and you get payload encryption as well. Again, my experience, I've, again, never seen authentication header used. I've only ever seen encapsulation security protocol used. Doesn't mean you won't see it, just that Ethan hasn't seen it. So, but there's a problem, a design problem, an architectural problem that we're presented with when we use ESP, Holly. One of the things that ESP or authentication header does, but it makes sure that the packet hasn't been messed with, right?
Yeah.
Okay, well, on a lot of networks, we have this thing called NAT, network address translation, right? What does network address translation do? Are you familiar?
Yeah, so that's taking usually your private IP and make it into a public IP. It's trying to get it across the internet. Network address translation.
What if your tunnel endpoints for your IPsec conversation need to go through a NAT box, some firewall that's performing network address translation? So that would be a little different from what you described, where you were using two SRX boxes that were directly connected to the internet. What if the IPsec was having to go through those boxes? Those boxes were not the endpoints, but they were a step removed. Now, my ESP conversation has to flow through a device that's doing NAT. By definition, NAT messes with the packet,
Yep.
right? It's going to get to the other end and go, something was messed with. This packet was messed with. That's no good. I'm gonna drop this traffic because it no longer passes my cryptographic checksums, my hashes, etc. I think something is wrong here because actually it's kind of like, oh, I just said but actually, that's funny, but it's sort of like a man-in-the-middle attack. Something changed this packet because there was a box in the middle that changed the packet on the way. The way around this is that's what the NAT-T is all about that we mentioned earlier. Network address translation traversal. I need this ESP packet to go through the NAT box but not be messed with on its way to its destination. And to accomplish that, it's effectively a tunnel. You're going to put a wrapper around the ESP packet with another network address translation traversal packet that you will see as UDP port 4500. And then, so you're gonna, the ESP packet's gonna hit your firewall that needs to do the NAT goes, oh, this is something I've been configured to encapsulate as NAT-T. It's gonna NAT-T it to the other side, which is gonna decapsulate it and then send the ESP packet unmolested to the IPsec endpoint on the other side. What do you think? How's that work?
It makes sense. It sounds a little ugly, but it gets the job done.
Oh, it's ugly. Oh, yeah. Yeah. I've taken an original packet, encrypted it, stuck it inside of an IPsec tunnel, and then stuck the ESP packet that is making up that IPsec packet, stuck it in another wrapper, and then shipped it across. And there's multiple layers of encrypt.
The poor guy on the other side is like, what is inside this?
Exactly. NAT-T is a special use case thing. Again, most IPsec tunnels are exactly how you implemented them, in my experience, where the firewall is already got the public IP address of the internet, the internet attached interface there, and that's what you're using as your tunnel endpoint. That's normal way to do it. NAT-T is like a tool in your toolbox that you use because it's like, I got this special situation. I can't do it the way I'd like to do it. Fine, we'll use NAT-T so we can get that ESP packet through the door unmolested, and working out. So, okay. So all of that was to talk through various components of the IPsec protocol suite that we've got. IKE, which you'll see is version 1, version 2, version 2 being, I don't think there's an IKE version 3 yet, is there? Gosh, I hope not. I don't think I missed the memo if that was it. I'd have to read about that.
We used version 2. I would assume if there was a version 3, we would have used it. So
yeah, I don't remember an IKE version 3 coming out anytime recently. IKE 2's been around a long time, but it made me wonder, like, oh, did they improve it again? But anyway, I missed that if that was the case. Anyway, IKE, authentication header, ESP, and then NAT-T. The things you're going to see most typically, IKE v2 as part of the setup. And then once the tunnel has been established, your SAs are going, your security associations are going and moving through that tunnel now. The tunnel packets themselves are going to be ESP, encapsulation security protocol, IP protocol 50. That's mostly what you're going to see on the wire in real life. All right. How are you doing now?
I've come across IKE. I hadn't come across or looked into all of those different things that you mentioned. So again, I preface this episode with, I have stood this up, but I don't actually know the little details of it. So it's good to know all these things. If I come across a situation that needs NAT-T, now I know. Otherwise,
now you know, right?
I don't know. It's going through, something's breaking, not sure why. It's being natted, that's correct. Well,
right, exactly. Now you know. Okay. The last point for us to make then is the two modes we mentioned earlier in the show, transport mode and tunnel mode. And again, tunnel mode is the normal thing that you're going to see in production. Almost always you're going to have implemented tunnel mode in my experience. But there is something called transport mode, and transport mode is the original payload protected with either authentication header or ESP. You could be either way, but it leaves the original IP addressing alone. And so what you're dealing with it is the payload.
Mhm.
You're making a decision about protecting the payload itself, but not the entirety of the packet. You're worried about the payload in the packet and using IPsec to protect that payload. If you want to take it a step further, you go into tunnel mode, in which case you are encrypting, encapsulating the entire packet inside of the tunnel. It works like a traditional tunnel would,
Yep.
and we've talked about tunneling quite a bit. So with transport mode, if you were to look at this on the wire, you would see the original source and destination talking to each other with their original IP addresses. Which, if you think about this from a standpoint of going across the public internet, if they're two private IP addresses that are not routable across the internet, this wouldn't even work, because those packets would get to the internet and the internet would go, I don't know how to route those. Those are not valid
Yeah.
IP addresses that I can route for. And so transport mode would only work assuming you're using private IP addresses inside of a network where all of those private IP addresses are known. Tunnel mode does the full encapsulation of that entire packet. So you can have private IP addresses, whatever, that need to talk to each other, get encapsulated inside of, and we've been talking about ESP packets that are using public IP addresses to get to each other. The public IP addresses, probably in your case, your example of the Juniper SRX firewalls with their public internet addresses. And that full packet is encrypted and carried inside of that ESP tunnel packet, and then decrypted on the other side once it pops out the other side of the tunnel. Now the private IP addresses are communicating. So a private IP address hits the IPsec tunnel, gets encrypted, encapsulated with the tunnel wrapper, sent to the other side, and then the reverse action happens. Yeah?
Yeah, I'm trying to think of a use case for transport mode, and I can't. I guess also I've never come in, like, if you haven't come into it, but I can't think of why I would want that.
You would use that because you work in a environment where you want to make sure an internal attacker hasn't messed with you in some way. One of the ways an attacker attacks your network is they will try to get inside, kind of establish a beachhead on some system inside, and then crawl around from there. They got in one system, now they're like, okay, where else can I get around to? And when they've inserted themselves inside your network that way, they will try to find ways that they can attack you. They might attack infrastructure specifically, try to break into systems and so on, but they will use the network and use packets and perhaps mess with packets as a part of their attack. You could use transport mode because maybe you don't need to encrypt the payload. That's fine. And you don't need to tunnel the packet because all of your packets are routable, and that's fine. You just want to provide some authentication. I'm talking to who I think I'm talking to, and no one's messed with this packet. And you can leave the original IP addressing alone that way. But I think a more modern way to do more or less the same thing is with MACsec. Have you run into MACsec before?
A little bit. I mean, I've heard of it. I've learned about it. I haven't actually implemented it myself.
I haven't actually implemented MACsec anywhere either, but in highly secure environments, there are switches that can do MACsec. If I remember right, and I didn't research this before the show, but to refresh my memory, but MACsec is actually an Ethernet frame that is being encrypted from point to point between two switches. It's the same thing. You're like proving the integrity of that packet and obfuscating it from one destination to another, so that if there is an attacker that's embedded in your network and they look at that packet as it goes across the wire, that Ethernet frame, it's been obfuscated, it's been encapsulated, it's been encrypted, and it's protected so that if you mess with it, it's not going to be considered valid when it gets to its destination. MACsec is designed for these sorts of highly secure environments, and there are the ASICs that are on the network switches are designed to be able to do MACsec at wire speed, as I understand it, incredibly fast. expensive hardware to pull that off. But if you need it, you need it. You're a financial institution. You're someone with highly secure information that you must protect at all costs. So those are the use cases where back in the day, maybe you would have used IPsec transport. I think, again, in modern days, you're probably implementing MACsec to accomplish that sort of thing. That would be the way I would expect to see that done. In 2025, I don't know that I can come up with a use case for IPsec transport specifically. Conceptually, yeah, but not practically with other competing technologies that are out there that do the job better.
Mm-hmm.
Okay, that's an intro to IPsec. And again, we crammed a 25-minute conversation into an hour as per our usual way of doing things.
Yep. Short and sweet, just how we like it.
I know. Oh, I know. Okay, so my question to you is, do we do another show on IPsec where we get into like the mechanics of what's happening when you stand up an IPsec tunnel? Do you want to do that?
I'd like to do that. We'll see if our listeners would like that, but I know that, sure, we've discussed the overarching ideas of it and what it looks like, but as a network engineer, we need to know how to actually set this up and go from there.
Okay, so you want to go full nerd. All right.
For sure.
All right. We can do that.
Always.
Yep, we'll have to I'll have to do some homework, and read up, refresh my memory on how some of this works. But we can walk through like, how does Ike do authentication, and what do the key things look like, and what is all this cryptographic stuff, and how does that? I'll tell you, it can get confusing because you can get buried in details on this stuff. What's happening with the cryptography and the roles that different the public-private key infrastructure and how that works. For example, and so on. There can be a lot to it. But I think without making it seem too intimidating, you can get your head around the fundamentals of it without, it's like you don't need to be a math expert to understand this. You need to know math is happening, but you don't need to know how to do the math.
Yeah.
Right? And so that takes a lot of the scariness out of it, and it's more understanding, what's happening at what stage, what Ike is doing, and what it expects, and why, like your mismatched networks because of a typo, how that can cause an IPsec tunnel to fail, and so on. Yeah, I think we can have that conversation for sure.
Yeah, I think it'll be an exciting one as well. I like to touch the surface and then go all the way in. So here we go.
Okay. All right, everybody. Well, thank you for listening to Holly and I chat about IPsec today. If you have comments, questions, or actually feedback on this episode, you know what to do. Send them to us via packetpushers.net/follow-up. That form sends your feedback right to a private Slack channel where Holly and I plan these shows together. It's the very best way to make sure your thoughts don't get lost in the mix. A whole bunch of you have used that. It's awesome. We really, really appreciate it. Like, share, and subscribe. Of course, we would really appreciate that as we try to make N is for Networking the most popular show on the Packet Pushers Network, which means I'm competing with myself because the most popular show on the network now is Heavy Networking, which is the show I began with my friend Greg back in 2010. So for N is for Networking to take over Heavy Networking, cool, that'd be a thing, but you can help. You can make that happen. We got lots of shows on the Packet Pushers Podcast Network. If you weren't aware, just search for Packet Pushers anywhere that you get your podcasts, or just go to packetpushers.net. Right on the front page, bang, every single podcast that we have on offer right now is there for you. Click through, find what's interesting, and all the subscribe links are there for your convenience. Last but not least, just remember, networking isn't hard. Other people figured it out, so you can too.